Alright, so in this first video, I think I am actually going to prove the mean value theorem. I said I was going to possibly do that in class, and I am going to go ahead and do it in this first video here. So let's go ahead and just write the mean value theorem down again. So mean value theorem is that if, well, instead of writing it if here, we'll say suppose f at x is continuous on a closed interval AB and differentiable on the open interval A to B. Then there exists at least one point C in the open interval A to B such that f prime at C is equal to f at B minus f at A over B minus A. And remember, this was my slope of, well, essentially it's the secant line, but it's the line connecting or going through the points A and B, and then that's a slope of a tangent line. So there's some tangent line in the interval A to B that has the same slope as the secant. And we looked at a picture of that and everything. So we're going to actually go ahead and prove this. But we're going to prove this by first just looking at a picture here. So I'm going to go ahead and draw another function here. So let me give us a rough set of axes here. And then we'll draw a function like this. And then I'm going to go ahead and put this as point A and this over here as point B. And then I'm going to do my best drawing a straight line through these. That's not good. Okay. And then we can clearly see in this picture that I am going to have some tangent line, like if I think about maybe roughly like right here or something. Well, that actually looks more like a horizontal, so maybe right here, you know, is where I have my tangent line that's parallel to it. So that's what I'm going to be trying to prove, is that I have this point C. So I'm going to erase, well, maybe I'm going to erase this. Come on, there you go. I'm going to erase those green stuff there because I don't really need that. Alright, but what I'm going to go ahead and do is label some things here. So I'm going to, first, I'm going to label this point here B, F at B, and this point here is A, F at A. And then the other thing I'm going to do is I'm going to call this line L at X. And then, of course, this is F at X. Now, the picture is what you kind of need to do this proof. And then you have to do, there's one thing we have to define here in order to do this. It's actually a fairly short proof. So what we're going to do here is we're going to define g at x equaling f at x minus L at x. Now, what we're going to do here is we're going to notice a couple things here. First off, g at x is continuous on the closed interval A to B. Why is it continuous? Well, it's continuous, I'll write here because f of x is continuous. We know that because that's given to us in the theorem. And L of x is clearly continuous because it's a line. So that makes g of x continuous. And I'm going to even just write this in kind of bullet point form. Well, then we know that g of x is differentiable on the open interval a to b. Well, we know that because f of x is differentiable on a to b. And again, we know that because it's stated in the theorem. And L of x is clearly differentiable I lost room for there, but clearly differentiable because it is a line. Because we know if we take a derivative of a line, we're just getting the slope of the line. Okay. Now, we're setting ourselves up to apply actually Rolle's theorem is what we're going to apply, because then what we're going to look at here is what is g at a. G at a would be f at a minus L at a. But let's go back and look on this graph. F at a is this point right here, but wait, that's the same point that's on the line. So this is equal to 0. Similarly, g at b is equal to 0. So this is the key thing here. So Rolle's theorem applies. And what does Rolle's theorem says? So there is at least one point C such that g prime at C, well, at one point C, I should put in here, in the open interval AB, such that g prime at C is equal to 0. So you get 0 is equal to f at C, I'm sorry, let's first just look at this. G prime at x is going to simply be f prime at x minus L prime at x. So we get g prime at C is equal to f prime at C minus L prime at C. So you get then 0 is equal to f prime at C minus L prime at C. But then we get f prime at C is equal to L prime at C. But remember, L is just a straight line. This is just slope of the line L at x. So if that's just the slope of the line L at x, what we really end up having is then f prime at C, well, the slope would just be f at b minus f at a over b minus a. So we've just proved the mean value theorem. So the mean value theorem is actually proven using Rolle's theorem. Now remember, for the exam, one of these two proofs could show up. Now, it's not a guarantee that these will show up, but you should definitely know how to prove Rolle's theorem and mean-value theorem. And again, one of the things you can do is in the course like this, I mean, later on if you go for like a math minor or something, you'll need to develop some more critical thinking skills, but for now you can just literally memorize these two proofs, and if they show up on the exam, then it should be easy points for you. Because if you just memorize what I've done, you'll know how to write the proofs down. And again, an easy way to memorize what I've done here is just to write it down several times, and then even speak it out as you're writing it down. Alright, so that's all I'm going to do in this video, but we're going to look at some other examples of applying the mean value theorem in the next video.